So it's 4 o'clock and we will start the seminar. Our speaker today is Alessandro Carotenuto. He is a postdoc here at the Institute of Mathematics of the Czech Academy of Sciences, and he will talk about the theory of connections for Jordan algebras. So if you have any questions, I'll be looking at the chat and I can ask Alessandro, or just unmute yourself and ask as we go. Okay, I'll give it over to Alessandro.
Thank you, Karen. And thank you, everybody, for being here, at least in a virtual form. So today I will talk about the theory of connections for Jordan modules. Before I shall talk about the differential calculi over Jordan algebras. These two topics were the main topics of my PhD thesis. And so here we have a plan of the talk. I will start with some historical overview that I think is very interesting and very needed in order to explain why we deal with Jordan algebras, why people started to deal with Jordan algebras to begin with. Then I will tell you something about Jordan algebras themselves. In particular, I will give you some classification theory for finite dimensional Jordan algebras. And then we will talk about the theory of representation for Jordan algebras. And we will see that the representation theory for a non-associative algebra is kind of different with respect to what we're used to. And then we will go to the two main topics, which are differential calculi over Jordan algebra and the theory of connections for modules over Jordan algebra. Okay, so a huge part of mathematics, the origins of Jordan algebras are rooted in physics, in particular in the axiomatization of quantum mechanics. So let's start with something that everybody knows. In quantum observables, in quantum mechanics, are usually given as the self-adjoint part of some sister algebra. And this works very well from an operational point of view. Self-adjoint elements have real spectrum, which is why they are needed to, which is why they are taken as observables in quantum theory, because we give, according to the Copenhagen interpretation, this, the spectrum of the observables, the spectrum of the elements in this sister algebra are the possible outcome of every experiment. However, this formulation seems unsatisfactory from a certain point of view, because we have here a huge structure of a sister algebra, and we don't have to use it when we are doing physics. For example, if X is self-adjoint, lambda X, where lambda is a complex number, is not self-adjoint. If X and Y are two self-adjoint elements, XY, the product XY is not self-adjoint unless X and Y commute. So it seems like when doing quantum mechanics in the sister algebra context, we are using some redundant structure. And this was the impression also of some physicists and some mathematicians in the beginning of last century. That's why Jordan started the program during the 30s. The program was composed of three parts. First part was to find the meaningful operation that can be done on the self-adjoint part of a sister algebra. Second was to find the most general algebraic structure that allows this operation. So find general. Entry was in fact, and point 3 was take this as the algebraic structure of observables in quantum mechanics. Okay, so for what regards point 1, he selected these meaningful operations. So if x and y are self-adjoint, the sum of two self-adjoint elements is again self-adjoint, sorry. I can multiply x by this time a real number, and lambda x will be self-adjoint again. This is just telling us that the space of self-adjoint elements is in fact a real subspace of the sister algebra. And then if the algebra is unital, also we will consider only unital algebra during this talk. And well, when I talk about algebras without specifying anything, I mean non-commutative of curves, but also not necessarily associative algebra. So if the algebra is unital, the unit is of course self-adjoint. And finally, I can take power of self-adjoint element, and the power of a self-adjoint element is again self-adjoint. Okay, this last property is quite important when we are doing quantum. Oh, sure. Okay, sure. So, okay, when we are dealing with quantum mechanics, we want to do spectral theory. This means that we should be able to write polynomials in the term. We should be able to write our observables as polynomials of some selected basis of observables, so to say. And this means that if we have powers of elements, we want if R is a polynomial that can be written as the composition of two polynomials in the variable t, we want that when we pass to the observables, the same holds. This is in fact equivalent to ask that these powers obey what is called power associativity, which is just the usual rule that everybody knows for the product of two powers of the same element. Okay, another important feature in quantum mechanics is that self-adjoint elements respect the formal reality condition. So this is formal reality, which means that the sum of two squares is 0 if and only if the two elements are 0 to begin with. So formal reality. And Jordan proved this theorem. So let A be a vector space such that for every natural number and for every x in A exists an element that we call x to the power n. Suppose now we define this product here with that I write with the bullet in this way. So this is what? This is 1/2. And suppose that A is formally real. Then these two conditions are equivalent. One, power associativity. And two, this identity here. This is known as Jordan identity. As we can see, this is somehow a weaker version of associativity, because instead of having x, y, and z, we have x squared, y, and x. Now, this justifies this definition. A Jordan algebra is a vector space A equipped with a product that we denote as bullet, such that x bullet y is y equal to y bullet x, so this is commutative. And the Jordan identity holds. Okay, maybe I erase here the while. Moreover, if the Jordan algebra respects the formal reality, so fy plus yx equals to 0, we say that this is an Euclidean Jordan algebra. Okay, so this identity looks ugly, and it has in fact some very ugly consequences. Let me just tell one. Suppose A1 and A2 are two Jordan algebras. Then we want to define the tensor product of A1 and A2. Well, and we want to define it in a meaningful way, in the obvious way. So the product of two elements is the component wide product. Well, this is a Jordan algebra. Is a Jordan algebra if and only if either A1 or A2 is an associative algebra. In general, the tensor product, the category of Jordan algebra is so badly behaved that the tensor product of two Jordan algebra doesn't exist. Yeah. Okay, so an ugly, an ugly equality with some very bad consequences. But this is not such an exotic object. We can build, in fact, Jordan algebra starting from associative algebra. And this is the first example of Jordan algebra that I can give you. So maybe, yes. If, sorry, if A1 or A2 is
okay.
so one of the two must be
Yes, sure,
associative,
sure.
otherwise, sorry. So let me give you some examples of Jordan algebra. No, I have to use this before. Example number 1, we start from an associative algebra A, and we build the Jordan algebra A plus with the bullet. What is the bullet here? Well, the product of two elements is now what is known as the anti-commutator. With some exercise, I mean, one can easily prove that this is a Jordan algebra. And so we have a definition. If A is a Jordan algebra such that
Ale, so there's a question coming in from our listeners. So V2 Check is asking, does the Jordan product have a quantum mechanical interpretation?
Yes, and in fact, this was going to be the example number 2. Okay, but well, it's on the way. It's on the way. Just wait a second. So, if we have a Jordan algebra such that exists to be associative in such a way that A is a subalgebra of B plus, so B with the new product given by the bullet, we call A special Jordan algebra. Okay, just. So second example, and this is why, in fact, we have a quantum mechanical interpretation of Jordan algebra. Suppose that A, the associative algebra A, is in fact a star algebra. So there are self-adjoint elements inside this. We can talk about self-adjoint elements inside A. Then the product of two elements, as I said before, of two self-adjoint elements is not self-adjoint. But if I consider the bullet product, now this element is self-adjoint. Why? Well, I take the star on both sides, and this is so yeah, in a way, if we want to give a product to observables in quantum mechanics, it has to be the Jordan product. Fine. Okay, no, we can. Okay, so third example, and this is obviously a special Jordan algebra according to this definition. Third example, suppose that we have a vector space V and F is a bilinear form of V on V. Then I can consider the Jordan algebra A F which as a vector space is isomorphic to R plus B, and where the product is given by this. So we have to okay. And as a matter of fact, also this kind of Jordan algebras are special Jordan algebras, so they can be embedded somewhere as elements inside an associative algebra. Okay, no, I move here. And finally, I can give you an example of an algebra with a Jordan algebra which is not special. But it is in fact exceptional. So example number 4, I guess. J83, which has vector space, is the space of 3 by 3 matrices with octonion entries, which are Hermitian. Why this is not special? Well, because octonions to begin with are non-associative algebras. And yeah, as a matter of fact, Albert, during the 30s again, proved that J83 is not special. Okay, just a second. And we refer to J3, which is called the Albert algebra, also as the exceptional Jordan algebra. And in fact, all the examples that I gave you are all the possible examples. In the sense, in the following sense, there is this theorem from Jordan, von Neumann, and Wigner. Every finite dimensional real Jordan algebra is the direct sum of simple finite dimensional Euclidean Jordan algebra. And I can give you a list of these objects. Just a second. So you have a list of the simple Euclidean Jordan algebras, which are given by JIN. I will tell you in a moment what these symbols mean. J spin n, J spin n, and J at 3. Here n has to be greater than 1, and here n has to be greater than 2. Okay, so here with JIN, I can take the value 1, 2, and 4. And with this, I mean real, Hermitian matrices with real numbers, complex and quaternions. Then we have J spin n, which are just a case of this kind of algebra, starting from, yeah, thank you, from a bilinear form, where we take as bilinear form the Euclidean scalar product, so the usual scalar product on R to the n. And finally, this is J3. So, as a matter of fact, aside from J3, all the algebras here are special. J3 is the only exceptional algebra. This is true for finite dimensional Jordan algebras, but in fact is true also for the infinite dimensional case. It was proved by Zellmanov, I guess, in the 80s. And so, yes, that's why people forgot Jordan algebras when they had to deal with quantum mechanics. Basically, all Jordan algebras can be thought as self-adjoint elements in some system algebra, from one can just deal, with exception of J3. There was at least no meaningful physical system which can be modeled using J3. So there is no reason to use Jordan algebra when using sister algebra is way more easy.
One question from Vita again. Why is there spin? That's the question. Why does spin appear in the name?
Why J spin? I guess it's a question about the meaning of the name J spin. I don't have any idea. Probably this could be related to the fact that the spin factors, this is the name of these guys, by the way, the spin factors can be embedded into the Clifford algebras, and so somehow they can be related to some spin structure over the manifolds, but I'm not sure of the reason of the name. But there is another. Sorry. So, you're welcome. Okay. So before passing to the representation theory, I have still to give you some definition that has to be restated when we deal with non-associative algebra, as in this case. So, some definition. First of all, the center of what is the center of an associative algebra? So we have to define, of a non-associative algebra, sorry. We define for every algebra the associator, which is just this symbol that makes the same job as the commutator. And the center of any algebra is the commutative and associative subalgebra of elements which commute and associate, I guess. Okay, this is not needed. Yes, this is fine. Okay, but it is equal to 0. With every other element of the algebra. And in particular, if A is commutative, this definition is in fact redundant. We don't need a commutator, of course, but also we don't need both of these relations. So it's just the elements that can be put in this first slot of the associator and give back 0. And so, okay, so this was the first definition. Now, if we take any algebra, any non-associative algebra in general, derivations of a non-associative algebra do not form a module over the algebra in general, but they do form a module over the center. This is not relevant for now, but will be in a moment. And so let's talk about derivations. Okay, so I will tell you just one thing since probably there is not too much time. As a matter of fact, Harris in the 50s proved that if xi, yi are a couple of elements inside the Jordan algebras, A, then this element here is a derivation. Moreover, and this is equivalent to second Whitehead lemma for Jordan algebras, if A is semi-simple and finite dimensional, for every x which is a derivation of the algebra, we can find elements in such a way we write x in this form. So again, xi, z, yi. Well, as I said before, non-associative algebras are very badly behaved. In fact, this, while for associative algebras, this form, which is the same form with the commutator instead of the associator, is unique. This is not true for Jordan algebras and for non-associative algebras in general. Okay, so part 3. I guess I will write here. So now we talk about representation theory. And we have to define modules over non-associative algebra. We can do it in full generality. So first of all, the definition that everybody knows of a module over an associative algebra doesn't work in, you have a question? No. Okay, does not work in the non-associative case. Why? Well, what is an associative representation? So we have some algebra A, and we have an homomorphism of A inside the space of endomorphism of some vector space. So we require in particular that phi of x, we require in particular this equality. For example, for a left representation. And we see, okay, so if we assume this definition for Jordan algebras, for example, we see that this is not a decent definition because we want, for example, to be able to represent the algebra on itself, acting on itself. So if particularly I take as a vector space the algebra itself, this requirement here is, and I take as representation, say the left multiplication, this requirement here is what is associativity. So the usual definition does not work for non-associative algebra. So what we do, we have to take another perspective. So suppose that the algebra A is in some category of algebra. With category of algebra, I just mean that the objects are all the algebra that respects some conditions. So we have the category of associative algebra, which respects the associative identity, the category of, I don't know, Lie algebra, which respect the Jacobi identity, sorry, and the category of Jordan algebra, which respects Jordan identity. To give examples, so suppose that A is in a category of algebras, we consider some vector space V together with two linear maps, lambda, okay, so, which go into V, and rho, which goes from V tensor A into V. Now we form what is called the split null extension, which has vector space is given by A plus V, and it is an algebra with the product given by xv times yw is equal to xy and the x w plus some rho y v. Okay, we take this sort of product on the non-split extension. Now, if A plus B is again in the category of algebras of A, we say that V is a bimodule over A. So if we specialize this to Jordan algebras, okay, now I want to write the maps lambda and rho. Lambda x on W. Sorry, lambda. Yes, okay. Yeah, thank you. Like this. Yeah. Yeah, okay. I wanted to mean, yes, these are inverted. No. Yeah, okay. Yeah, the point is that this is going to be the left action of the algebra. This is going to be the right action of the algebra, and I was just going floppy. I've been floppy writing. Thank you. Okay. Now, let's specialize this to Jordan algebras. So first of all, Jordan algebras are commutative algebras. This means that elements inside the split null extension should be, I mean, the split null extension by a module of the algebra should be commutative again. This means that I can write this. Then every module over Jordan algebras is in fact a B-module, and it is a symmetric B-module. So I will confuse the terms module and B-modules from now on. And what else? I have the Jordan identities. And okay, let me just write what are the consequences of the Jordan identities for what on the action of the algebra, for what regards the action of the algebra on its module. These are written as this way. No, there is no operator. By L of X, I just mean left action, which coincides with right action anyway. Okay, so some example. Well, example number 1, if A acts on itself by multiplication. Well, I mean, we defined the module in a certain way that this happens. And in particular, if A is equal to J3, this is the, I mean, so, okay, just a second. So we call A the regular module over A, and we say the same every time that we consider a module of the form A tensor E with the action given on the first component, by multiplication of the first component. And as a matter of fact, every module over J3 is regular. Number 2, sorry. One example, one genuine example is Hermitian, the Hermitian matrices which I write in this way, I denote in this way, are a module over the Hermitian matrices. That's Cy, so X is an Hermitian matrix. And it, okay, not just matrix, an Hermitian element in every system algebra. So X is Hermitian or self-adjoint. We consider it an Hermitian element, and we take the star. We take as product the anticommutator. And this is, okay, and we have, basically what we have, we change these two guys, and the minus appears. What did I write? Okay. And okay, maybe I can give just these two examples because I guess we're running out of time. So now we can pass to one of the two main topics of the talk, which is differential calculi over Jordan algebras. And I go to this blackboard. Okay, before introducing the differential version of differential calculus, I should tell you what is a Jordan superalgebra. No. So, definition. A Jordan superalgebra is a Z2 graded vector space which is a commutative superalgebra. So we have a bilinear product such that xy is equal to -1 to the product of the degrees of these two guys times yx, and which respects the Jordan identity. Also, then we can define an n-graded Jordan superalgebra, which is a Jordan superalgebra with another grading on n this time, on the natural numbers. So it is the direct sum of this vector space omega n, such that omega n times omega n is inside omega n plus n, as usual. Okay, so finally we can give the definition of differential calculus.
Multiplication here is not assumed to be associated in the differential calculus.
The multiplication here is not associated.
Because
It's
yeah.
It's a differential calculus for a Jordan algebra. So the multiplication is respects the Jordan identity. But yeah, thank you for the knowledge.
And then with the Leibniz rule,
I still have to define the differential calculus. But yes, the Leibniz rule is the usual graded Leibniz rule that we have on differential calculus. So
okay, sorry, I thought this was the definition you were going
no. It's okay. Definition: differential calculi over a Jordan algebra is an n-graded Jordan superalgebra omega like sum of omega n together with the differential. So okay, and here every omega n is a modulo over a fixed algebra A, and we have a differential. So we have the Leibniz rule. And we have that the differential is first important. So usual definition. And we have one particular example of, I mean, in general, it's quite difficult to build differential calculi over Jordan algebras. For example, we still don't know about examples of universal differential calculus for Jordan algebra. But we have one good example, which is given by derivation-based differential calculus. How much time is left? 10 minutes, okay. So, oh, okay. Okay, I can, okay. Okay, good. Good to know. So the derivation-based differential calculus is given in this way. We started by defining one form. So A is the Jordan algebra, and omega 0 coincides with A, and omega 1, okay, so maybe let's subscript here, are maps from derivations of A into A. and how we define the differential. Well, the differential goes from omega 0 into omega 1. So dx. Okay, so this is an element of the algebra. I'm making it, and I'm transforming it into a map from derivations into A. So I have to tell you how it acts on a derivation X. And this is just given by the derivation acting on the element. Then we can extend this to a differential calculus.
The maps from the derivations are just linear maps from the derivations?
Yeah, just linear maps, yes. As it is in usual commutative geometry. Okay, and now we take omega n derivation, the space, sorry, the n component of omega are n antisymmetric linear map. Oh, no, sorry, I told you something. They are not linear. They are linear maps with respect to element in the center of the algebra. Okay, you can just take linear maps, and it is the same for simple Jordan algebras. But in general, the most general thing that you can do is taking the linear maps, which are
okay. Yeah, so they're modular maps over the center.
They are modular maps over the center.
Which
yes.
Then in the commutative case, because the center is everything. I guess for a manifold, we reduce down to short one forms.
Exactly. Yeah. Thank you. So lambda n. So I should put this subscript here. Okay, I don't know why. But into A. And I use the usual Chevalier-Eilenberg formula to extend the differential calculus from first order differential calculus to all the differential calculus.
So then it's unique, basically, just like Chevalier-Eilenberg.
The derivation, yeah, the derivation based differential calculus is unique. Yes, exactly. It is unique, but I mean, there is one instance in which it has one more nice property, which is the case of the exceptional Jordan algebras. In fact, what we proved is the following. If I take the exceptional Jordan algebra J at 3, I have this result. I shall use this again. It's a lot to get used to this. So, what? But there is no ordinary eraser here. Oh my, okay. Okay. So, if we take as Jordan algebra, the exceptional Jordan algebra G at 3, and omega d is any differential calculus over J at 3, then there exists a unique, it can be realized as an extension of the derivation-based differential calculus in the following way. There exists, and sorry, and also we require that there is an algebra homomorphism between J at 3 and the zero component of omega. Then there exists a unique extension of phi as map of differential calculi. So from derivation-based differential calculus over J3 into the differential calculus omega, such that this map commute. I don't know if I. Okay. Okay, so maybe I can write briefly a sketch of the proof of this. So to prove this, you have to use the fact that that every module over J3, as I told you before, is a regular module. So sketch of the proof. Okay, we start to use the normal thing. So, okay, omega is a module over J3, but this means that it is regular, that we can write it as J3 times some vector space here. But also we know that omega is a graded graded super Jordan algebra. So the second thing that, so if one proves the following, and we have done it, if one proves that J3 times E is a super Jordan algebra, if and only if E is an associative superalgebra, then we write, now we can write the differential calculus as omega equal direct sum of J3 times e to the n. And okay, so we take a basis A alpha of E1, and now we write every element. We can write every element. Okay, and we take a basis of the derivation of we take delta k is a basis of the space of derivation of J3, and then we can write every element as every differential in this way. So it says kappa, it says alpha. And now the unique map phi is defined in this way. We take phi on X tensor theta kappa, where theta kappa is the dual element, is the dual basis of del kappa. Well, this is just E kappa, and we see that this is the only map that extends, this is the only extension of phi. This is an extension of phi, and it is unique for how we have defined it. Okay. Finally, so this is all we know for now about differential calculus over Jordan algebra.
To summarize, so basically what you're saying is that for J8,
for J3,
there is a universal and it's the derivation.
There is the universal differential, yeah, and it is the derivation of the differential calculus.
So some of what you were saying earlier on, it's not that universals don't exist, it's just that you don't know.
Well, For now, we know that existed for one very specific Jordan algebra. I don't know if it exists. I mean, we know for sure that the derivation-based differential calculus does not have this property for special Jordan algebra. You lose, for example, the unicity of the extension if you consider a special Jordan algebra. You can build a counterexample in which there are two extensions of this map phi, where is it, of the homomorphism of the algebra into omega 0. So yeah, in general, we don't know if there exists a universal differential calculus for Jordan.
Sorry, I find it difficult to think about non-associative things. So what happens? I mean, because if it's associative, then the map has to be unique. But it's somehow the multiplication messes things up.
Yes, somehow it's the Jordan things gets up by the Jordan identity. Always. Yeah. It's no, it's a long. It's quite long to build. No. I don't remember it completely. Yeah. Okay. So, last part of the talk is about the connection of our module. So we have defined the differential, and we can now define connections. And this is part 4, I guess, of the talk. 4, 5. Okay, since we don't have time, I will just deal with the derivation-based connections. So let them be, sorry. Let them be a module over A. We have two equivalent definitions of a derivation-based connection. So first definition, we consider the space, the graded space omega der n of m, which is given by, say, so omega n are anti-symmetric linear map from derivation of the algebra into its module. And okay. And so now this is not just a module over the algebra. This is in fact a module over the differential calculus, the derivation-based differential calculus of the algebra. And we are so a connection.
Wisi profesor Lipkowski, który kompletnie też nie wie, co ma zrobić. No.
A connection is a map from omega der m into itself, which is of degree 1. So and which respects the Leibniz rule for connection. So where omega is an element of the differential calculus over the algebra, and phi is in omega there of m. And so this was the first definition of a connection. We have a second equivalent definition, a connection, so second definition. Okay, in this case, the curvature is defined just as the square of nabla. Then we have second definition. Which is nabla is a map from derivation of the algebra into endomorphism, linear endomorphism over the center of the algebra of the module.
N and the -1, I don't know.
Where?
And the down here. The
Yes, thank you.
Yeah.
Thank you. Which respects, now we write the Leibniz rule for connection as nabla x of what? Of an element m. Okay, so we let y act on m. Ym plus y nabla m, where now y is an element of the algebra and m is an element of the module. And now, where do I write? The curvature is given by this tensor, so it's R. It has to be evaluated on two derivation and is given by this object. Okay. Okay, these two definitions are equivalent, but I guess I don't have time to show you how they are. I can finish with the two examples of connections over Jordan models. So first example is pretty easy, but we can. Okay. So first example, M is a regular module over the Jordan algebra. Then we can define. Okay, so from both the definition, one can see that, for example, we take the second definition, which is important for me. If I have two connections, nabla and nabla prime, then their difference is going to be an endomorphism of the module. I mean, a module endomorphism of M. So if we take as a module, a regular module, one example of connection is given by what is basically the differential on the algebra. So we write every element inside here as a tuple, a1, an, and we define D, evaluated nabla x as D A1 dAn evaluated on the derivation x. So this is one example, one connection on the module M, and every other connection is given by adding an endomorphism of the module to this guy, right? So all we have to do is to characterize endomorphism of a free module over a Jordan algebra. And we have done that. So if M, I guess, proposition. Okay, we have to suppose now that A is a unital Jordan algebra, and if M is equal to A times E, for every module endomorphism of M, there exist elements in the center of the algebra. So we denote them by, I don't know, lambda J into the center of A. And the real matrices Mj of R. So we call phi this endomorphism of the module, such that phi evaluated on one tensor V is equal to sum of lambda J times Mj V. Okay. Okay, we have to add one of these guys every time we want to take a connection over a module, over a regular module on a Jordan algebra. By the way, I'm calling them a regular module and not free module because these objects are not, because again, Jordan algebras are so badly behaved that these things are not free, in the sense that I cannot obtain every module as a quotient of a regular module. And this is, I guess, the definition of a free object in a category. And okay, so this sums up all the theory of connection for regular modules. But we can do more. We can define for every finite dimensional semi-simple Jordan algebra, we can define a base connection, which is a good starting point. In fact, recall, I have taken every possible eraser. Okay. So if M is a module over A, semi-simple, which is semi-simple as algebra and finite dimensional, we build a connection in this way. We know that for every derivation of A, we can write it in this way. So no, we will say it here. Then we define nabla from derivation of A into in this way by taking nabla x applied on M is defined as sum of xi, z, and yi. Okay, so this is a connection over the module M. It is just to pure. Why is it easy to prove that it respects the Leibniz rule of the connection? Because in this case, the Leibniz rule of the connection coincide with the Leibniz rule, the real Leibniz rule for the algebra given by the split null extension of A by M. So that algebra that we wrote before to define a module. And the first thing that one has to prove is well-posedness. Yes, these connections are well-posed, and this depends by the fact that we are considering only spatial Jordan algebras, because basically for the exceptional algebra, we don't have a case in which M is different from a regular module. So A has to be a spatial algebra, and in particular, A plus M is going to be a spatial Jordan algebra, and well-posedness of this connection depends on the fact that we can embed the split null extension into an associative algebra. And as a matter of fact, also this connection is a flat connection in the sense that the curvature is zero. And this again can be proved by using the Jacobi identity into the associative version of the split null extension. And I guess this is the end of the talk. Thank you for listening.
Okay, thanks very much, Alec. Very nice talk. Do we have any questions from the audience? Feel free just to unmute yourself, or you can just type up the comments and I'll announce it.
But you can show on the screen maybe. Oh. No, this works for special Jordan algebra. It works only, I mean, I guess the question, okay, already. Okay, fine. Okay, sure. Well, the center, so what are the center of the algebra and derivation for JA3? Okay, first question is very easy. The center is just real numbers because JA3 is a simple Jordan algebra. So it's just given by multiples of the identity. While the derivation of JA3 are given by the exceptional Lie algebra F4. So yeah, these are the derivation of J3 are the exceptional and welcome. So as I said, they maybe derivation of J3 are given by the exceptional Lie algebra F4.
So maybe I'll ask another question. And so you said the connections you were actually able to produce, for examples, were all flat.
No, I said that this connection is flat. Then if I add some them, this is a base connection. To get another connection, you add a modular endomorphism of M and it might or be flat or not. In particular, if we look for connection over the regular modules, flat connection are in one-to-one correspondence with Lie algebra homomorphism of of the algebra of matrices with the algebra of derivations, with the Lie algebra of derivation of the Jordan algebras we are dealing.
Okay. And so another question. So for for J8 3, there you said basically the derivation calculus operated as a universal calculus, basically. So not classically, sorry, in the associative world. In the associative world, there's what the Kunz-Quillen theorem that says that you've got a connection with respect to a module admits a connection with respect to the universal calculus if and only if it's projective.
But then every module over J3 is regular, which is even more than projective. I mean, regular module are what you will call free module.
Yeah. Okay. Okay. Sure. Okay, so it seems like there were no more questions. So we'll thank Ali again for his talk. And yeah, thank you all for coming. And next week there will be the seminar by Conrad Aguilar talking. Well, I don't think we have a title yet, but we should soon. Okay, thank you.
It's going to be on the pod list sphere, but yeah, the exact title we don't know yet.
Quantum metric spaces on the pod list sphere then. Okay, thanks, Justin. Yep.